All right, folks, I got some old school 311 going on. Check out these lyrics. Doesn't amaze me. Yeah, that was cool. Some old school 311 from the 90s. 6 protons, 6 neutrons, 6 electrons is encoded in this planet we live on. That's carbon, right? 6 protons, 6 neutrons, 6 electrons. We just got done talking about all of that. All right, cool stuff, folks. Okay, so I want to spend just a little bit of time talking about nucleosynthesis and the origin of the elements. All right. So this is really cool, and this is at the end of the chapter, so I'm kind of going a little backwards, but I just wanted to talk about this for 1 minute. So we have the Big Bang, or we theorize there was a Big Bang, right, which created everything. Okay. And we notice here 10 to the minus 10 seconds. That's like 1/10 billionth of a second. Protons, neutrons, and electrons started forming. Okay? And those protons, neutrons, and electrons were able to combine. So look at this chemical reaction. So this 11P and 10N, those are the chemical symbols for proton and neutron. So it's the same with the mass number on top and the atomic number on the bottom. A proton is just one single proton. So this 1 and 1 says it's just one proton. So I'm going to write that down. You should know those symbols, right? 11P equals proton. So 10N is neutron. The N for neutron, but we also know that it has to be a neutron because the 1 tells us there's 1 proton plus neutron. The 0 tells us there's 0 protons, so it's all a neutron. And then finally, when we say 0, let's see here. Let me rewrite that. We say 0 minus 1 E, and that's our symbol for electron. Okay. So now this proton and neutron combine to form what we call a deuteron. Okay, so that's the combination of a proton and neutron. And look, if you imagine, we know that our nuclei of atoms are made up of protons and neutrons. So this is really like how we first start to begin to create nuclei. Okay? And now, so what started happening is very quickly then after that, hydrogen and helium were able to form. Okay? So a very simple nuclei. But as it turns out, that's really where nucleosynthesis kind of cut off because there wasn't enough energy to keep fusing these hydrogen and helium into larger atoms. So this is why about 99% of the universe is hydrogen and helium only. Okay? Because once all this hydrogen and helium was created, all this material is getting flung out. Okay? And there was really not enough, pressure, gravity, energy, whatever you want to call it, to keep fusing these hydrogen and heliums together. Okay, so it wasn't for about another billion years later, between 300,000 and a billion years later, that atoms started to form through stellar nucleosynthesis. So in other words, all of these stars and galaxies started forming, mostly comprised of hydrogen and helium. And at that point, there was enough energy in those stars and star clusters to fuse heavier nuclei together. And so, for example, this is showing you, so this is an alpha particle, okay, which is the same thing as a helium nucleus, okay? And if you look at how these numbers work, right, 3 times 4 gives you 12. 3 times 2 gives you 6. So as these heavier nuclei were able to fuse, they were able to start creating the elements carbon and boron and oxygen and nitrogen, and eventually all the way up through iron, right? Iron 56, okay? So there was a huge lag in the evolution or the origin of the elements. And to this day, it's why 99% of the universe remains to be hydrogen and helium. Okay? So I'm going to move forward and get into the naming of compounds. So naming compounds is going to be a pretty major aspect of this course. So I'm only going to give you one lecture on naming compounds, but this is something we're going to be working on throughout the entire semester. So I want to make sure that you're making a good effort right away, a good initial strong effort to learn how to name compounds. Okay, so I'm going to go through this one by one and then summarize at the end. So naming, and all the naming we're going to do in this class is on inorganic compounds, okay? And I'll talk about that at the end. The difference between inorganic versus organic, okay? We're just focused on this for this class, okay? And so there's a couple different types. So the first we're going to focus on is covalent. So covalent is going to have a different naming scheme than ionic, okay? So binary molecular compounds, so binary, meaning compounds consisting of two, in this case non-metals, that makes them covalent, okay? So we first look, so for example, my example that I have is SO3. And the first thing we do, we look at the very first element, okay? And we just name it as is, sulfur, okay? Easy, okay? Just read it right off the periodic table, sulfur, all right? The second element name is changed by adding the suffix "ide." So for example, we note the second element is oxygen. Oxygen will become oxide. Okay? And then now we have to look at the quantity. Remember, respect the subscript. Okay, right? We look at the quantity right there, and we use prefixes to identify how many of those atoms are present. So 3 means tri, so it's sulfur trioxide. Okay? What if I had this one? Okay? Well, sulfur, and it's oxide, there's a 2 right there. 2 is di. So this would be sulfur dioxide. I'll give you another one, 2 examples that you already know. Okay? CO and CO2. Okay? And note, on the very first element name, okay, if there's only one of them present, we don't say mono. Okay? Here's this list, right? 1 is mono, 2 is di, 3 is tri, etc. But let me just back up for 1 second. We don't say monosulfur trioxide. So it is implied with the first element, no mono. Okay, only. So now what about these two? Carbon monoxide, monooxide. Okay, you can say carbon monoxide. You know carbon monoxide, the stuff that comes out of your tailpipe. Don't suck it in, right? Okay, what about CO2? Carbon dioxide. And sorry, I'm writing these all together. These are 2 words. Carbon dioxide, carbon monoxide. Okay, so let's go to this other example here, right? Okay. Do not use the prefix mono when naming the first element, like I just said. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We really won't even get much past like 7 or 8, to be honest. But here they all are. Okay. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca, undeca, dodeca. Yes, you have to know these. Yes. You have to know these. Make some flashcards. This is not going to be the only table in this list that I tell you have to know these, so you have to make a bunch of flashcards. Okay? Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca, undeca, dodeca. Okay? So prefixes ending with O or A are modified when used with elements beginning with vowels. Okay? So for example, we note that deca, right, is D-E-C-A, but what about when used with oxide? It's not decaoxide, it's just decoxide. Okay? Or same with the carbon monoxide. It wasn't monooxide, it was just monoxide. Okay? So if you have O or A, you modify those with elements that begin with vowels. So oxygen is a good example of that. Okay? So P4O10, and look, now there's 4 on this phosphorus. So 4 is tetra, so tetraphosphorus decoxide. Okay? Let's keep going. There's going to be lots and lots of examples for you to work on with these. Okay, so that was covalent compounds. Here comes ionic compounds. Okay? Ionic compounds. So binary ionic compounds consisting of a cation, which is usually a metal, and an anion, usually a nonmetal. Remember, we talked about that in the previous lecture. Ionic compounds are metals and nonmetals. Or in other words, the leftmost side of the periodic table combined with the rightmost side of the periodic table. And so when we write these, it's order specific. So it's always going to be cation first, anion second. Always cation, anion. Okay? The cation, you just name it straight up. Magnesium, sodium, whatever, right? No changing the name. No dies, tries, penta, none of that. You don't do any of that in ionic compounds. Okay, this list, covalent only. Okay, tattoo that on your forehead. Covalent only for these prefixes. Okay? So let's go back to ionic compounds. Cation, anion. Cation first, anion second. Cation is just straight the name, magnesium. The anion, we put an "ide" at the end also. So that was similar to what we did with the covalent. Okay? We put an "ide" at the end. So chlorine would become chloride. Bromine would become bromide. Even oxygen can form covalent compounds, but oxygen can also form ionic compounds. Oxygen also, similarly, just like we did before, oxide. Okay? So formulas for ionic compounds must always be neutral. So we talked about how magnesium, it's one of the elements in group 2. Okay, let's just fast forward to my periodic table. Right, look, there's magnesium. Look, it's in this row where things are always 2+. This row, things are always 1+. Okay? So we have to know that. There's going to be nothing in the formula that tells us about magnesium being +2. We just have to know that it's +2 from the periodic table. Okay? And we also know from the periodic table that the halogens are always -1. So there has to be, we'll say 2 times 1 minus. It has to be neutral. In other words, the charges have to add up to 0. Okay? So in ionic compounds, we're just going to say the name of this compound. The name of this compound, MgCl2, it's just magnesium oxide, or excuse me, magnesium chloride is the name of this compound. That's it, magnesium chloride. There's no di, tri, tetra, etc. with the covalent compounds. So ionic compounds are a little tricky because we have to recognize, like if someone just says magnesium chloride, so suppose someone just tells you the name, you have to be able to work backwards to figure out that it's MgCl2. If somebody tells you that it's MgCl2, you have to also be able to work forwards that it's magnesium chloride. So be able to go back and forth, okay? And so that means you're going to want to know all of this stuff, all these charges, right? I circled the red. The red charges you should know, because that's how you're going to know how to make compounds out of it. I mean, look, there's Mg2+, there's Cl-, so we have to have 2 of these chlorines for every 1 magnesium to make an ionic compound out of it, okay? So let's keep going, okay? And let's talk about the transition metals, okay? So transition metals, right, that region in the middle, they are variable. Their charges aren't always set. Like, for example, here we can see iron comes in 2 forms, 2+ or 3+, okay? So for metals that form cations with different charges, so that's transition metals, a Roman numeral is used to indicate the charge of the cation. So for example, if I have FeCl2, okay, we have to do a little bit of math to figure out the correct name. We know that chlorine becomes chloride, which is 1 minus, okay? And if I have 2 of those, right, if I have 2 chlorines, that means I have 2 minuses, okay? So that means my iron has to be 2 plus, okay? And that's going to give me iron 2 chloride. So I would actually read this by, phonetically by saying iron 2 chloride. And that 2 tells me the charge on iron is 2 plus, which tells me I need 2 of these Cl minuses. Okay? So there's something I want to address right away too. Okay, look, when I'm going to write this, 2 Cl minuses does not equal this. Nope. Don't do it. 2 Cl minuses does also not equal this. No. Big no. Okay. But 2 Cl minuses, 2 Cl minuses definitely equals this. 1 Cl minus and another Cl minus. Respect the subscript, okay? And so when I have this 2 down here, what it actually means is I've got an FeCl and an FeCl, right? I've got 2 chlorines bonded to this iron. So keep track of all of that, because some of you are going to screw it up, and that's okay. You're learning, you're beginning. But keep track of this. 2 Cl minuses does absolutely not equal Cl2 minus, okay? 2 Cl minuses absolutely does not equal Cl raised 2 minus. But 2 Cl minus definitely does just equal 2 individual Cl minuses, okay? And then when I allow them to bond with an iron 2 plus, this is what happens, okay? Or iron 3 chloride. So we recognize that we would have 3 single chlorides. So I would have to have an iron charge of 3 plus to give me iron 3 chloride, okay? So keep that in mind. Look, there's copper 1 and copper 2. There's manganese 2 and manganese 4. There's vanadium 3 and vanadium 5. So we kind of have to use information about our formula to know what charge we have. So for example, suppose I gave you this formula right here, VCl5, and I asked you to name the compound, okay? So we look at this and we recognize that chlorines are always -1, and there has to be 5 of them. So this has to be vanadium, and don't write out the word 5. This was my phonetic. It's vanadium 5 chloride, okay? Okay, I'm going to move forward. I know I'm going through each one of these quick, okay? So make sure that you're practicing, and I'll point out resources of where you can practice, okay? So here's just that same info that I showed you, but just now with a table. And you don't have to memorize this because the transition metals are all variable. You never know which flavor you're going to have unless you see it bonded to something. Then you know what you have. So for example, if you have iron with 3 chlorines, you know it has to be iron 3. But if, for example, you see iron with only 2 chlorines, you know it has to be iron 2, okay? So don't memorize things when you don't have to. And here's just kind of a list so you can connect how this all works, okay? And no, this is not a full list at all. These are just some of them, okay? So moving on. Okay, so now we get to another aspect of naming, the polyatomic polyatomic ions. Okay, poly meaning more than one. So these are ions containing more than one atom. You need to know this whole list for this class, front and back. You need to know that nitrite is NO2 minus. And also, you need to know that NO2 minus is nitrite. Okay, so hopefully all of my text here is clear. Please reach out to me if it's not. So you can see all of those little charges should be superscripts. So sulfite is SO3 2 minus. Okay, I'll just write that one down. So it's 3 oxygens, and the entire thing, I'm going to put a circle around it and say the entire thing is negatively 2 charged. Okay, that's how these polyatomic ions work. So nitrite, for example, is an N with 2 oxygens bonded to it, and the entire thing is -1 charge. Okay, I'll put like 1 negative just so it's clear. All right. So these polyatomic ions, they are, as you can see from this list, mostly all anions. Ammonium, NH4 plus, there's a cation. Mercury 1, and this one's kind of confusing. It's Hg2 2 plus. That's why it's called Mercury 1. It exists as a diatom, but it's positively 2 charged, meaning each mercury is +1. Okay? And I'm going to go through a systematic naming scheme for this: perchlorate, chlorate, chlorite, and hypochlorite. I'll talk about these ones specifically in the next few slides. Acetate, CH3COO minus. Make flashcards. You got to know the name, the spelling, the formula, the charge, all of it. Be able to connect it all. Okay? And what I also want you to recognize, these polyatomic ions, they're basically one thing. Okay? I know it's like, in the case of sulfite here, it's 3 oxygens and a sulfur, so that's 4 atoms, but it exists as one thing. That's negatively 2 charged. Okay, that's why they're called polyatomic ions. So how do we use the polyatomic ions? Well, we can name the polyatomic ions just like we did with the other compounds. Okay, with the other ionic compounds, because remember, these are charged. So because these have a charge, they have to form ionic compounds. So I'll give you an example. Suppose I write this formula: NaNO3. You might be thinking sodium, nitrogen, trioxide. That's not it. I'm going to write that down. Sodium, nitrogen, trioxide. That is not it at all. Okay, that's not what the right answer is. All right. So I'm going to put a big X through this one. Okay, no. So what is it? Well, it's definitely sodium. Okay. But now look, we've memorized our list and we recognize, oh, look, nitrate is NO3 minus. So that means this compound, I don't know why my eyes don't like to show up the first time I write them. So that means this compound is just called sodium nitrate. As simple as that, sodium nitrate. Because the sodium is Na plus and the nitrate is NO3 minus. Okay, so they make a perfect pair, NaNO3. What about another example? I'm going to do that down here. I'm going to write Na2SO4. Okay. So we can see that sulfate, oh yeah, sulfate is SO4 2 minus. So it makes sense that we had to have 2 of these sodiums. And remember, when I break this down, this all means 2 Na pluses, not Na2 plus. Respect the subscript. You're going to hear me say it over and over again. So this is 2 sodium pluses plus 1 sulfate. Okay? And I simply call this compound sodium sulfate. No tri, di, tetra, anything, because it's an ionic compound. So because it's an ionic compound, I don't use the di, tri, etc. I just have to know what the charges are. That's how ionic compounds work. You just have to know what the charges are. Okay? So make sure you also practice with these polyatomic ions. There's another one I want to point out that's probably familiar to you. Look, peroxide, and look, it's O2, 2 minus, okay? If I combine that with 2 hydrogens, because hydrogen is always plus 1, so if I have 2 minuses and I combine this with 2 hydrogens, then this is called hydrogen peroxide. Hopefully you know what hydrogen peroxide is, okay? You've maybe had to use it on a cut a time or two, all right? Let's continue. Okay, so the next group of compounds you have to know, binary acids. This is going to be very similar to your ionic compounds, okay? So binary acids always contain hydrogen, always, and a monoatomic anion. Okay, so mono meaning 1, okay? So for example, if I have HCl, okay, the first thing that I do with binary acids is hydro, and then the halogen-based name, which is chlorine, except for now I don't do "-ide", like chloride, right, for the ionic compound. Instead, I do "-ic". "-ic". So it would be hydrochloric acid. Or in the case of HBr, hydrobromic acid. And so the way we know that we use this scheme is always hydrogen. Hydrogen is always present in these binary acids. Okay? I'll give you another one. What if I want to make a binary acid out of sulfate? Okay? So we recognize this is the polyatomic ion sulfate. I recognize that hydrogen is always plus 1. Hydrogen always is going to be plus 1. So how many of these hydrogens do I need? If you said 2, good job. Remember, respect to the subscript. H2SO4. So that's hydrogen and sulfate. That's going to make hydrosulfuric acid. Hydrosulfuric acid, okay? Sometimes we can just call this sulfuric acid, and that's okay too, okay? I'm probably giving you a bad example here because technically that's for binary acids. So we're just going to call this sulfuric acid. Sorry about that. I got confused. Okay, sulfuric acid. So with the binary, with the monoatomic, that's where we use the hydro. So let me give you one more example. So if I did HI, we know I is a monoatomic ion. Okay, so H2SO4 is just sulfuric acid. HI would be hydroiodic. Okay, so just to clear that up, we only use the hydro when it's the monoatomic ion. Okay, I can make acids out of these polyatomics, and then at that point I just say sulfuric acid. We're going to come up, I'm going to give you more examples of these polyatomic acids as we go. Okay, and I think I have some of those next. Haha, here we are. I have them next. Okay, so here's the series of oxoanions. Okay, so let me go back here and say oxo acid. Okay, not a binary acid. Okay, so oxoanions or oxoacids. All right, so the series, here's the polyatomic ion that I told you. Perchlorate, chlorate, chlorite, hypochlorite. There's kind of a fun game that you can play with these. So like now I'm forgetting the game. So the 8s are bigger because they ate the extra oxygen. if that makes any sense at all. So perchlorate, chlorate, chlorite, hypochlorite. Okay? When I make acids out of these, look, I don't put the hydro. I just do the ic. And I only do the ic for these two, perchloric and chloric. Now the ites become us. Chlorus, hypochlorus. Okay? So make sure you're flashcarding it up. Know this list. All right? Okay. So here's a big summary of everything we just did. I know I went through that awful fast. Okay? Which is why I definitely 100% want you to practice. Practice makes perfect. Okay? Go through the homeworks. Go through your book. There's tons of these practice problems in the book. Okay? And if you want even more practice naming compound problems, just reach out to me. Okay? I think in week 3 discussion, we'll get into naming compounds. So we'll have a practice worksheet for you next week. So here's a nice flowchart. Okay, naming compounds. Is it ionic or is it covalent? You have to recognize which is which to get this right. Okay. Remember, covalent is all nonmetals. So I shouldn't say like all nonmetal compounds are covalent compounds. It is made up of all nonmetal atoms, right? A covalent compound is made up of all nonmetal atoms, and the ionic compound is one metal plus one nonmetal. So that's the first place to start, is recognizing is it ionic or covalent. Okay? If you recognize that it's covalent. Okay? So another question it's asking, is there a metal or ammonium? So ammonium is this kind of exception, and I'll talk about that in a moment. So they're putting this example here because ammonium is one of our only polyatomic cations. Okay, that's why this is here. So if the answer to this question, is there a metal? No, that means it's covalent. Is there a metal? Yes, that means it's ionic. Okay, so let's suppose we have a covalent compound. So is it an acid? How do I know if it's an acid? Well, does it start with hydrogen? If it starts with hydrogen, then yes, it's an acid. If it doesn't start with an acid, then it's not an acid, and we use the number of each atom, mono, di, tri, etc. We don't put a mono on the first one, remember. So carbon monoxide is not monocarbon monoxide. It's just carbon monoxide. And write that second one, add "ide" to the second atom name. Okay? So now what if this is an acid? Yes, that means it's got hydrogen. Hydrogen plus what? If it's a halogen, okay? Hydro something ic acid, hydrochloric acid, hydrobromic acid. Okay, but what if this hydrogen is with a polyatomic ion? So then we don't use the hydro. Instead, we either say ate, ite, ic, or us. So it could be, if the ion name is ate, it becomes ic. So if it's nitrate, it becomes nitric acid. So for example, nitrate, which is NO3 minus, becomes nitric acid. Or the other example I gave you, sulfate, write that SO42 minus on the previous slide, sulfate becomes sulfuric acid. So what if it's an ite, like nitrite? So nitrite is NO2 minus. This is why you're going to make flashcards, right? So that you know the difference between nitrite and nitrate. So nitrite becomes nitrous acid. Okay? So that's covalent. So now what about ionic? Okay. So always positive ion first. What is the positive ion? So if it's ammonium, that's the exception. You just say ammonium because ammonium is one of our only polyatomic cations. Okay? So I'll just remember cation. Okay? Okay, so what if it's a type 1? So type 1 meaning it's one of the representative elements, not a transition element. Okay, so type 1, use the name of the atom, just straight up. If it's sodium, call it sodium. If it's magnesium, call it magnesium. Calcium, barium, etc. Okay. So then now, what is the negative ion? Okay. Keep going, and if it's monoatomic, add "-ide" to the end of that negative ion. Okay, well, if it's a polyatomic, okay, we have to use that ion name. And here it's also giving you another way to remember hypo is one less O than ite. 8 is one more O than ite. Okay? Or you can just memorize those polyatomic names. And if it's, what's the positive ion? If it's type 2, we use a Roman numeral for the ion charge. And we have to use the formula to help us figure out what the charge is. Okay. So, now I'm going to wrap it up here, okay? So be able to name compounds, ionic and covalent, given a formula. So if you were given a formula, come up with a name. Also, if you were given the other way around, if you were given a formula, be able to come up with its name. So go back and forth either way. Okay. Know the formulas, charges, and names of polyatomic ions discussed in class. All right. So I know that was fast, going through this naming compounds. So that's why you're going to practice, do the question banks discussion next week, not September 1st, but September 8th. We'll go through like a naming compounds worksheet and discussion. Okay, folks, you know how to find me. I'll see you around.